Broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to Rockwell's webinar with Chris Lummer Giddens on designing and building high-performance homes with stone wool. My name is Dan Edelman. I am the Key Account Manager with Rockwell, working with builders and contractors nationwide. Without anything further to do, I would like to turn it over to Chris to begin his presentation. Take it away, Chris.
All right. Thank you, Dan. Dan, can you hear me okay?
Yes, you are crystal clear.
Great. Thanks. Well, welcome to this webinar. It's a real pleasure to be talking to all of you from around from wherever you might be. This is going to be a presentation about designing and building with stone wool. And I was glad to be invited to present this to you. This is based on a lot of experience that we have using this product, but we'll talk about, I want to go through the sort of the journey that we went through to get to where we are today, and how, and then towards the end we'll get into some case studies and what we've done, showing you the projects that we've worked on. So and we'll look forward to your questions at the end. So I am one of two people of LG Squared. My wife, Jody, started the business in 2006 in Florida. She started doing renovations, additions, and new construction in the Tampa area. And things were going really well until about 2008. I was working with a high-rise condo firm down there, and the economy took care of that, and I was out of work, and Jody was still, hanging on to the business for a bit. And then we found our way to Atlanta, where things were still going a little bit. And then we, in about 2010, the firm I was working for felt the effects of the downturn and had to let me go. And I met a local building science or a retired physics professor by the name of Allison Bales. He has a company called Energy Vanguard. I worked with him for about 2 years and did a lot of residential HVAC design and building science consulting, and did a little bit of helping with some of the education there. And that really kickstarted a lot of getting into the high performance world of construction. And I've got my degrees from University of Colorado, Hawaii. Those are all architectural degrees. And I grew up as a builder's son. We built a few homes together, and he taught me belts and suspenders approach to absolutely everything. So if there were 2 or 3 ways to do, to brace a wall, we would do them all, just because we wanted. And he was, a couple of the houses we built were for ourselves. So he was always teaching me how to strap it down and make sure that thing doesn't move. And that ties into high performance and durability quite well. So once I finished college, and we went out to Hawaii and got some historic preservation education there. And then when I was in Atlanta, when I was working with Allison, got my HERS training, which is it's a rater training that helps, it rates homes, and you get into blower doors and HERS certifications and that. And then also did some earthcraft rating for a while. A lot of HVAC designs throughout the world. I've gone into the Bahamas, Canada, outside of the U.S., but most of it primarily in the U.S. And then really did a lot of consulting with building science. Worked with architects, homeowners, builders, and did that for a while until things really started to pick up, and people were looking to build from scratch. And so they sought out our company, LG Squared, to design these homes, and we were designing high performance homes that nobody really knew how to build. So our clients were asking us, hey, who can build this? And we we talked around and we decided, well, I'll just get my builder's license. And so we started building these, and that's what we've been doing ever since. So I've been interested. I wanted to do construction and being an architect from day one. Building science has become my niche, my specialty. We have our blog and YouTube channel talk a lot about the building science of what we're doing, and so we continue that to today, and it seems to be very useful. A lot of our clients come to meetings, and they know more about my videos than I do. They've studied. They do these. A lot of the clients are very into their research, and we get a few engineers here and there, and they just love the idea of something that can last a really long time. So that's a little bit history there of LG Squared and where we are today, and we'll get into this presentation now. This presentation is hosted by Rockwool. And basically what they're saying here is that we were not, my opinions here are my own, and that I was not influenced by the Ducati motorcycle, the iPad Pro, or the lifetime supply of Fruity Pebbles sent to me by Rockwool, and that Rockwool doesn't necessarily endorse my company, my views, or me unless I talk about their product. So, or you can just read the screen, and that's really what this disclaimer is. So let's have some fun and let's learn something here. So, like I said, we haven't always done high performance homes, and we started getting into this, as I said, with in about 2010 when I started learning about building science more, and it sort of became fairly intuitive for me. Most of the principles were straightforward. Physics was a struggle for me in college, but I certainly, in terms of how physics applies to construction and a lot of the science behind it, I really just I was able to do it fairly quickly, understand it. And so the first home we did that I worked on was when I was still working with Allison, and we did a home. At that time, there were a lot of incentives from, the stimulus package fueled a lot of incentives for new construction or renovations and swapping out old HVAC systems. So we would, we got a lot of calls for those kinds of things, and we would do manual J-load calculations and to help them get a rebate. And then eventually it turned into more of a, we want a whole house. People were the economy was starting to do better, and they said, we want something from scratch, and they realized with their research, that they could have a house that was, that used less energy, was more comfortable, lower maintenance, lasted a lot longer, and it didn't have to be an above ground basement with a single window. It could actually look really nice, and didn't have to look like anything other than just any other home out there. So the first home that we and then we'll get into sort of the science stuff just a little bit, just to sort of show you how we got to where we are today, understanding things like thermodynamics, hygrothermics, which is we'll get into that, and then designing the perfect wall. Once you understand these principles, coming up with an assembly that works basically anywhere in the world. And with that perfect wall, you're going to have a perfect wall, roof, and floor, and so continuity is absolutely critical, and which leads to the topic of airtightness, which means, this is one of the, after bulk water control, airtightness is absolutely the number one, or it's the number two control layer. So it's critical. And then why we do it and how we do it. And then, so we'll go through a few of our projects to show how we went about it, some tips and tricks, and some of the challenges, opportunities that we had, and the successes as well. So as I said, our first home was when I was with Energy Vanguard, and we did, this is Energy Star was starting to really make a big presence in the industry, and people were wanting to get their homes certified and proven that they have something that is using less energy. So this house was a tear down to the, they wanted to tear it down to the foundation and use the original footprint, and we found some cracks in the foundation. So we ended up just going down to just ripping it all out and starting from scratch. It just saved the builder quite a bit of money to try to, instead of repairing and then just to go ahead and do something new. So this is in a historic district, so it had to follow their design guidelines. And you can see it's very more classical design here. And at the time, I was, spray foam was sort of a silver bullet, and it sort of continues to be that way for a lot of people. And so this is a 2x4 construction, and the cladding is, fiber cement cladding over we have an air gap there to help control moisture, to get the ventilation, to keep the assembly ventilated well so it performs as it should. We have some zip system sheathing, which it's a wall sheathing that is with an integrated water resistive barrier, and and then of course fill the cavities with open cell spray foam. And then in the below grade assembly, we have a closed cell foam, and this is just a crawl space. A lot of the equipment's down there. There is an ERV. We use mini splits, ducted and ductless mini splits in all of our projects. And so this has a ducted mini split in the crawl space, and then one in the attic serving the adjacent floors to them. And here we're talking about mentioning continuity. Here's a good look at what we're starting to do here. We go from crawl space up into the wall. That right there, all of your control layers, which I'll talk about in a minute, are continuous from foundation to wall and then wall to roof. This assembly here is just, as you can see, is 2x framing with open cell foam filling the cavities, and then a zip system sheathing before you put the shingles on. So this is the first home. We did achieve a 0.8 ACH50. For those of you who aren't familiar with that, that's just air changes per hour at a pressure of 50 pascals, which is basically a 20-mile-an-hour wind blowing on all sides of the home. And that just tells you how much leakage is happening in the building envelope. And this is 0.8, which is the volume of 80% of the volume of the house is exchanged with the outside air per hour at that pressure. So obviously your house isn't under that pressure all the time, so you're not exchanging that much every day. But but that's just how they measure it. It's just it's almost arbitrary how they came up with it, but that's the metric we use. This is in Georgia. It's in Atlanta. It's in the historic Grant Park, which is climate zone 3A. Most of our homes are in the southeast. Well, all of the ones we'll talk about today are, and we go up to North Carolina down to Florida with our projects. So anyway, so this one, we were using with the spray foam and the zip system sheathing installation, we were able to achieve this airtightness here, and that, again, super important on any home. And this is another one here in Georgia. This is, it has a name, Proud Green Home. It was sort of a media home. They had a lot of manufacturers contributed to this, so we got a lot of the products were donated for it. There was a lot of press around this one. You can search Proud Green Home and see a lot of information on this. It was done in, which is just south, it's near the airport here in Atlanta. And anyway, we used 2x6 walls here and advanced framing techniques. This is a lot of the Earthcraft and Lead for Homes, those programs. They they tend to promote the use of more efficiency in the materials. So when you use 2x6, you can go 24 on center, which gives you a lot more insulation because the wall has less of the framing and less often. So we'll talk about thermal bridging here in a little bit, but this is so with 2x6, and then we put on the exterior a product called R sheathing, which is their standard zip system sheathing with 1.5 inches of polyisocyanurate, and that's attached to the exterior, and it is a structural sheathing. And then we put another layer of the it's not called out here, but it says this 1x4 furring strips. Excuse me, this is actually a Benjamin Obdyke. It's a rain screen mesh that goes in behind the cladding. So the roof is filled with just a 12-inch TJI. And then your just standard zip system sheathing over the top there, and then a standing seam metal roof. And here we again transition from foundation to wall, continuous insulation. This is a slab on grade, so we used a stem wall, and we covered that stem wall with a below grade insulation, and then continued up into as the zip system R sheathing. And so here's that below grade assembly. Again, in climate zone 3A, we were able to get down to 0.7 ACH50. And a lot of that is, really just execution. There's not extra product or material that's necessary. It's just execution. All of the products that we used are very typical in this home and most homes. And it's just following the manufacturer's instructions, and of course just paying attention to every crack and detail. And we, during our blower door tests, we now use a fog machine, fill up the house with fog, do a positive pressure test and then any fog we notice coming through cracks, then we go attack that crack or gap and we fill it, and then we know where our leaks are. This next project this was in about 2014. We started getting into using a different insulation product on the exterior. And the reason we started going to the exterior is because of what we'll talk about in a bit is, thermal bridging. Each one of these studs in the wall is a thermal bridge. So in order to control the heat loss through the studs, we're putting and all the framing, we're putting insulation on the outside. So this is our second experience at using exterior. And then in this case, we actually did use 1x4 furring strips, and then of course a fiber cement cladding here. This house is actually is net zero. There are times when she's net positive, but this is about a 6 kilowatt system, and you can see it's perfect orientation, lots of sun, very little shading. So this system is working really well for her. But we filled the walls with loose fill fiberglass, and this is starting the transition away from foam. So this is a product by Owens Corning. That we also filled. It's basically the exact same assembly on the roof. So the wall is the roof, is the floor. That concept of continuity that is super critical. So this is our 2x10 roof, 2x12 roof framing to get extra insulation in there, and then just 2 layers of XPS. And we did that primarily to be able to control air movement through this double layer here. So if you stack it basically one over the other, you've got an air gap at the seam. And so we staggered them both horizontal and vertical to be able to limit that airflow. And then we, of course, sealed it well with the tape. This is a very tedious assembly right here because there are 2 layers of 1/2 inch. It's worth it when you go to a much thicker assembly because they don't make, super thick exterior insulation as one piece. So you almost are forced to go with multiple layers. I wouldn't do this again, just 2 layers of 1/2 inch, but it was exploratory. This is another product where the manufacturer gave us this insulation to try out, this assembly. So we did it, and we won't be doing that. We don't recommend it because it's just so time consuming. So a lot of this has to, a lot of where we are today has to do with what we've learned about cost as well as installation and performance. This one we got down to 0.9 ACH 50 in the same climate zone. So after those 3 projects, we were getting, during that we were of course learning more about thermodynamics and all the other science, other building science principles. So this idea of thermodynamics is, high pressure, low pressure, and it's always going to go from high to low. The analogy I thought of back when I was learning this was, hey, because we spend a lot of time as architects, we spend a lot of time in in meetings, and sometimes those meetings get tense. And what do? You run out of the room. I want to take a break. You go to a low pressure situation, go by the, just walk around the office and cool off a little bit. High pressure to low pressure. It's always the way it does. Unless something else exists at that moment, it's always going to be high to low, hot to cold. So this principle right here is huge. It guides a lot of why we started drifting toward putting exterior insulation to the outside, because we can now protect, not only keep the occupants warm, but it can protect the materials of the home. The structure of the home is now protected by layers of insulation that are, and all of we are drifting towards putting all of our control layers to the outside. And I'll define those here in a little bit, but this idea of of hot to cold is what drives a lot of our decisions here. Hygrothermics is a term dealing with drying potential. Okay, and so this is when you have a high pressure, with the low pressure, the water is going to find its way to the lower pressure. It's sort of like when you have condensation. If you think of Allison taught me this analogy. If you have at a hotel where they have the little porte-cochere, you park your car under the porte-cochere roof overnight. Your car will be the roof of your car will be dry, where all the cars in the parking lot are going to be wet, and the condensation is happening because it's losing its heat to the night sky. The night sky is a heat sink, so it's pulling all of the heat from the earth, and as it does that, when it reaches a dew point on the surface of the roof, then you start to get condensation. The car under the porte-cochere you're not losing that heat nearly as fast, and so there's no condensation happening there. And so this drying potential this is not only important for, it's important to keep moisture, to control that moisture the way you want to. If an assembly can get wet, this is some stone wool here that it sat on overnight. This is in Florida. When we were building our tiny house, we set this 2-inch piece of rock wool on a subfloor overnight. We hadn't done, and it was a Florida storm, a lot of rain, and it filled the top 1/4 inch of this stone wool board. And we lifted it upright, set it up here on this ledge here, and within 20 minutes, the whole thing, all of that water, which we calculated to be a couple of gallons, completely emptied from that piece of insulation. And it's not just, and most of the time your assemblies aren't going to get this wet, okay, unless there's a real problem. And so the moisture that gets into these assemblies is going to be maybe some through some of the gaps in the cladding, but mostly from humidity, airborne moisture. And so when the moisture gets in there, it has to be able to dry and get out of the assembly quickly. And so this idea of hygrothermics is what's behind this. Is you have to understand that to be able to know how your materials are going to work and how they're going to be able to dry out and perform. Because any insulation, everybody knows, most people are aware that any insulation that gets saturated is not going to perform the way it's supposed to. So this is water is something we want to keep out of our buildings, and it is as some people may have heard, there are the three leading causes of building damage are water, water, and water. So this is number one, and then air tightness is number two. So taking these principles, we started to come up with our own idea of what a perfect wall meant. This concept of a perfect wall, we've heard it from what some people call him the father of building science, Joe Stiebrick with Building Science Corporation. It wasn't his term. He uses it a lot. He teaches it a lot. But it has been around for a long time. And so what we're trying to do as designers, which is what we do when we're, as architects, we're designing these buildings. We're designing the building science as well. So it's not just the aesthetics of the home and the functionality and it's designing the assembly so that it works, so that it lasts. And, just like we have to understand scale and proportion as an architect, when we're designing assemblies, we need to understand hygrothermics, thermodynamics, and these principles are just as important. So I mentioned control layers, and in the upper left there, you see we have 4 primary control layers, and that's water, and then water, air, vapor, and heat. Those are the 4 main control layers, and you put them, and you see in this assembly, everything is to the outside of the structure, and this is our preferred way of designing and building, because again, for continuity of our insulation, there's absolutely, in all the homes I'm going to show you, we have absolutely no insulation in the cavity except for one project. And so everything is to the outside. It becomes, and we're finding now that the installation of exterior insulation is actually less labor than trying to get the cavity insulation installed correctly. And if you know about correct installation of bats, it takes a lot of work to get it right. You're cutting around wires and boxes and making sure that it's flush with the studs. You don't have depression, and you don't, every time you depress the insulation, compress it, and you have more than 5% compression, then you're starting to lose the R value. And there's published data showing how much the R value changes as you compress the insulation, every a certain amount. So with it all to the exterior, you don't have that, you're not losing, it's straight. This is all rigid insulation that we're using here. And labor, it's just like stacking bricks, you've got either 2x4, 4x4, or 4x8 sheets, and they just stack up, and it goes up so quickly sometimes, and especially on the roof where you're just almost walking on depending on the pitch, you're just walking on a floor there, and you just run it along. And it just becomes anyway. So that's something we'll show, but that we're learning that install of exterior versus cavity is simpler in our experience. So these are things we look at too. When dealing with this exterior insulation, you see here is a comparison of 2 layers of exterior versus everything in the cavity. And what we're looking at on these diagrams is what is our sheathing temperature. And sheathing temperature matters because if it is cold, if the sheathing is cold, it can this is where the condensation can happen. And this is what we look at when we're looking at, I'll talk about this here. This is a hygrothermic analysis, and it shows us where our risk level is for moisture. So when we get to this, when we have a sheeting temperature close to the inside, we're less at risk of having any condensation buildup because we're not reaching dew point here. Whereas if we have a wall with cavity insulation, our temperature here, this is in Western North Carolina, showing a sheeting temperature of 18 degrees. And if you reach dew point, you're going to have condensation on the sheeting. It depends on where, it just depends in this cavity on where that condensation happens as to how damaging it can be. You know, your sheeting can, if it stays saturated for too long, it can start to corrode. So this analysis here, this is from one of our building science friends here at Rockwell. Actually, he does these, will do these for us. And so what it shows is this here, this green line is our threshold. We don't want our moisture risk to reach this level. And so you see, these are the different assemblies that we had on a particular project, and we were just sampling each one. This, the one that has the least risk, the further away from this green line, that's the right balance of insulation on the exterior. Nothing, and these, same thing here. We were just looking at different options for the amount of insulation. So this is the exterior side of the sheeting layer, what the RH is, and that's this spot right here. And then the water content in the sheeting layer, the moisture percentage, that's what this is here, and it's showing us that we're well below our threshold. So this is our risk line, and we want to stay. And this, by the way, as you can see, this is over an entire, from 2016 to 2019, showing worst case scenario for 3 years. So each one of these peaks is it's the same time of year here. So this is just showing the worst case scenario on the home in a certain assembly, and showing that we are well within our well below our risk level. So this perfect wall, as I mentioned, it can be done anywhere in the world. These projects we've done, and what changes is the amount of insulation. Everything else stays the same. We put all of our air and vapor control layers right on the exterior side of the sheeting. I can go back to this right here. This is where our air and vapor control layers are. And then we put our thermal control layer out here. And then our bulk water control layer is the cladding. And so we want to make sure that is solid and robust, so we don't get any bulk water into this assembly. But as I said, especially with the right insulation, with a drained, vented cavity, which is a rain screen, we can allow water to get in there because it dries. So this is the idea of a perfect wall, and this is what we have designed as our perfect wall that continues to work today. So again, anywhere in the world, this assembly, the control layers to the exterior, the way we've got it, can work anywhere. So continuity, without taking this perfect wall and continuing it to the roof and to the floor, you start to have, you can risk having a failure in that enclosure. So if you, as you're building up these layers, everywhere that there's a potential for a break in that layer, you have to address it and make sure that everything stays continuous. Here we are with those control layers shown, and this is just a schematic of what I'm talking about: the wall, the roof, and the floor, all being continuous and wrapping the entire structure like an igloo, like a cooler. You have this is our perfect assembly. This diagram on to the right here is from a project that we are finishing up building right now here in Atlanta that we've got 7 inches of stone wool on the roof and 4 inches on the exterior on the walls. And you can see it's just absolutely continuous. We've created overhangs to the outside of the structure. So we've attached them to the sheathing and they cantilever out, and we just ran the insulation out here. And that helps us with keep our temperature the temperature of our framing regulated as well, because without the insulation wrapping the outriggers, they will expand and contract differently than our fiber cement, and then we start getting gaps and cracks where we don't want them. So that's why we decide to continue this overhang to the exterior. And we'll show another project later where we didn't have any overhangs, and it just became this sort of this principle here, the continuity, form followed function. So the function is keeping the insulation continuous, and then the form of the building was informed by this function. So I'm not going to feel bad about mentioning airtightness over and over again. It is just absolutely critical. We want to, if we condition inside, we want to keep that conditioned air in, and we don't want the bad air to get in. So keep good air in, bad air out. Having absolute air tightness, it does control humidity. Every project that we have here in the Southeast, which we are known for high levels of humidity, we don't have a single dehumidifier in any of these homes, but with one exception, and that has to do with the system that we used and the size of and the frequency that the building is being used. So we're using, a ducted versus a ductless. The ductless doesn't have the same moisture removal capacity as the ducted do. So we did put a dehumidifier in there, but these homes have been tested we've been monitoring them for a few years, and we've had 0 issues with relative humidity in the homes. And I attribute that primarily to the air tightness and the proper sizing of our mechanical systems. So with air comes moisture. And so having an airtight building, you control how much moisture is getting into the home. Heat loss and gain, that's with air, you can also carry heat. Moisture carries heat and air carries moisture. So by creating an airtight shell, you're controlling heat loss and gain. Critters, we found our tiny house in Florida, we don't have, cockroaches are aplenty down there, and we don't get any in our home. We've seen one come through the front door because we left it open. Pollution, obviously, that's the bad air, so we want to keep that out. The house we just finished, we are actually about to finish, and I'll show you some details there. We achieved a 0.05 ACH50 there. That's correct, 0.05, which is about 10. I guess that's 10 times the allowed, 10 times tighter than the allowable by the local building code. And this house right now, we've got a small dehumidifier running in there, and yesterday was super high humidity, so it's pretty warm. Our HVAC crew came in to do their finish up to install the outdoor unit, and when they walked inside, they said, "Hey, do you have AC running in here, because it's quite cool?" And it's because the building shell is so tight, we're not allowing, and the doors are shut, so we're not allowing that moisture to stay in, and whatever moisture is in there is being evacuated by this dehumidifier. And it's a small one you get from Ace Hardware, so it's not anything commercial. So why do we do it? These are only 7. There are many reasons we're doing it, but some of the key things that drives us to using stone wool as this exterior insulation is we're in our in a project we did in North Carolina. It's an off-grid home. It's in the mountains, a lot of forest fires there. So fire resistance is huge. I mean, stone wool has been used as a fire blocking for a long time. And it's, only recently has it been used as building insulation in a big way in more recent years. And so fire resistance is a real thing, whether you're in the city or in the mountains. It's a big deal. And so we love that aspect about it. Of course, the drying potential, as I mentioned, once I saw that piece of insulation in Florida, how quickly it drained that water, I was just sold forever. That type of that ability to insulate, to dry out, to resist fire, and to resist, and I'll mention it ahead of time, but resist bugs. It's and another, if you're used to foam insulations on the exterior, you'll find that there is some expansion and contraction with those products, those plastic products. And whereas this rock wool has very little, if any, expansion and contraction. And so we don't end up having those gaps that you can see right here in this slide. All of these seams right here are potential, movement of air. Now, this is an air permeable insulation, but it does have, it isn't perfectly, it does have some air restriction to it. It doesn't allow air to just freely go through. So these would be where we would have airflow, if any. And so that's why again, you see the staggering that we're doing here. This is the second layer of it. And the back layer has a seam in the middle. So this is appealing. UV resistance. This stuff could sit out for a while and exposed to the sun. If it's used behind a vented rain screen, it will have exposure to the sun. So having a highly resistance to UV is very beneficial for our projects. And bugs and critters don't care for it. I've heard of some cases where you might get some burrowing in there, but that's if you leave it in the wrong spot for extended periods of time. But in a home, we haven't seen it. Bugs just don't eat it. So it's very, and then durability. This is rock. Rocks have been around for ages. And so because of that, we know that it holds up to all conditions. And as I mentioned earlier, it becomes pretty easy to install. In this image behind, they're using more screws than they needed as they started building up the wall, they realized they don't need to put as many in there. And so it got easier for them. This was their first time doing this. So as they started building up the wall, they realized how simple it could be, because this next layer could just be stacked on top of this without maybe one screw in there. That's what we're finding. All right, so let's now we'll get into some of these projects and some of what we've learned, mistakes we've made, and how we are where we are today. The first one is a project I mentioned already, the tiny house. We did actually do a combination of cavity and exterior on this one. This is in Central Florida, about an hour north of Tampa. And it's about 600 square feet with the loft, but the footprint is about 400. So it's more of a cottage than a tiny house, but it's still low volume. And so when you see this number 0.2 ACH 50 on a volume this small, that's a lot. That's easier to achieve on a much larger home, because again, this is based on cubic feet of the home. So again, 2 inches of exterior over zip system sheathing. We got our zips. We spent a lot of time on this layer right here to get every crack, gap, and hole and penetration sealed up perfectly. This is a stone wool batt insulation in the walls, and then 2 inches on the exterior, a 1x4 furring strip for our rain screen, and then a metal, that's a standing seam metal cladding there, and then the roof is the same standing seam metal. And here's a shot of the exterior. This is the furring strip here. All of it's horizontal because we needed to do that for the standing seam. And the airflow happens, there is a gap. The standing seam actually bows out just slightly. So there is a gap that allows the airflow past the furring strips. This floor is something we were experimenting with because it was our own home. We could do this. I'll show you some pictures of how we did this, but you can see that it's the exact same assembly as the walls, just turned 90 degrees. And so we filled cavities here with insulation on the bottom side, and so everything is all at the exterior. This is the hygrothermic analysis of this of the assemblies here, and this shows you where our the sheeting temperature here drops about 50% between the drywall and the sheeting. The temperature drops to the sheeting, and then we drop even further. 42 degrees is the design temperature there, the coldest about 1% of the year. And so that's what this looks like. We're, again, looking at all these factors in deciding what assembly works best. And so we dip a little bit above our threshold here, but we're not at risk. This is a very short period of time. And because the assembly can dry out, because the insulation is very vapor open, we're and very has a high drying potential. We're not concerned about this. This shows without the exterior that our sheeting temperature would be closer to the exterior, so we may experience some condensation there. So this is like I said, it's an experiment. We built the floor upside down so that we could have that continuity in the sheeting. Otherwise, this is a stem wall here. And so because instead of putting the framing right on top of the sill plate here and then butting the sheeting up to the sill plate, the house right here, you can see a cantilever and this happens on both ends of the home and on the front and on the back of me. And so we have that, you can see there, the sheeting just continues sitting on top of the framing. So it's not interrupted. We're not having to deal with that intersection of the beam meeting the sheeting. And so we flip this thing using, just pulling this thing slowly, one section at a time. Again, this is very tedious, and we've come up with other ways to handle this, but this worked really well because it was a small house. Certainly wouldn't recommend it on a large one unless you had a crane. But this is, again, trying to get that continuity. And so it was fun. It was a labor of love, but it worked out. We did, deep 2x12 flooring just so we could get plenty of insulation and still have room for all of our utilities without having to interrupt the insulation much. And then our, little details like this is where it happens. This is where it matters. This is a hurricane clip. This is the zip system on the bottom of the floor structure, and this is going down to the sill plate. And then we just dress that with a lot of zip system sheeting. There are liquid flashing to seal up that penetration, and that happened at every single one of them. So it's a little tedious, but again, that's where it pays off, is paying attention to every little detail like that. This showing the insulation on the bottom of the floor on the exterior, and then here we are with the insulation in the cavities of the floor, turning that insulation up here at the edges so that it's connected to, when you build the wall on top of it, it does continue, so your thermal control layer continues. This is the floor meeting the wall, the insulation overhangs down below, and then we'll install the exterior below. The This is showing that all of our air and vapor control layers here with the zip system sheathing. This was the start of, you can see every nail is covered with the liquid flash. Yes, it can be tedious. It's not necessarily required. Manufacturer doesn't require that. We did end up doing it on the roof because we didn't, with all the rain that we had down there, this is our preferred method to treat the roof, just attacking every possible leak for air or water. And again, horizontal furring strips. This is the whole thing wrapped in the insulation. Now we're ready for cladding. This structure here is built separately. It's not actually attached to the structure. So the ledger board is on the outside of the insulation. And we do all of our decks and roofs like this. Okay. This is showing, the wall before we insulated the roof. Just some more details here. Again, continuity of insulation. And getting ready we got this part up here. This is just structural strapping here, and that goes on before the insulation. So that, again, stays within the control layers there. This is in North Carolina. This one's got down to 0.5 ACH50, and this is an image from an article we did in JLC, the Journal of Light Construction, where we're showing here the zip system running on top of our ceiling joists. These are 2x10s, and then we filled up on top of that. We created this platform, which made it easy for the framers they had something to stand on here when they were stick building a roof. And so this whole area here is just filled up with R60 insulation, and we did 2 layers of like a bat, and then we did like a loose fill stone wool insulation on top of that. And so this right here, this detail right here made it possible to be as tight as we were, but then we had this continuity. Their energy bills are the highest they've seen, and it's a 3,500 square foot home. The highest they've seen is about $100. The average is around 50. And they're conservative, and so they probably keep the temperature not extreme, but they don't crank it. But they one time tried to use their wood burning or the gas stove or gas fireplace that I told them they didn't need. They used it, and within 10 minutes they had to turn it off because it was just too hot. It's just the house contains that heat really well. These are the hydrothermic analyses for this home, just trying different assemblies. And you can see here listing the different assemblies we tried: 5.5 inches in the walls, because this is a 2x6. That you can see up here, we only use 3.5 inches of insulation. This gives us room for electrical, a lot of plumbing, a lot of the utilities can happen in this part of the cavity. So it makes it a little more flexible, a little easier to work with here. And then, so we explored different options there: 2 inches on the outside, 3 inches, and then different varieties of cavity. And so we ended up with the 2x6 wall, 3.5 inch bats, and 3 inches exterior. And here shows, with this combination, our sheathing temperature between 18 and 60. And, this is, again, North Carolina, up in the mountains. If we hadn't done exterior, our sheathing temperature would be closer to 18 on the design temperature. And here again, this is the roof or the deck structure isolated from the home. It's a standalone. We do have a bolt, a couple of attachments through this column into the structure here. Very minimal thermal bridging with those attachments, and we of course sealed it extremely well as it penetrated. So it's very trivial, the amount of penetration, but at least for the most part, we don't have a continuous thermal bridge with the ledger, and that's how we've designed and worked around that. And then this is the front porch. It's a front stoop, so it's a concrete stoop here, and you can see we put 2 inches in between it and the wall. Actually, that's 3 inches to prevent that thermal bridge. Concrete, metal, the most conductive materials that we build with. So it's really important that we keep concrete away from our structure to prevent that thermal bridging. This was our electrician's favorite job ever. They had zero, when they're doing a ceiling, they didn't have to work. These aren't IC rated. They're not, we're able to just install and not worry about the insulation that's going to go, not have to, it was so easy for them to install everything from electrical to any plumbing that would run through. So it worked out really well. They loved it. This is the off-grid homestead that we did in Western North Carolina. There were 4 buildings. This one in the image here is a barn. All of them no more than 0.5 ACH50, this climate zone 4. This one has the most we've ever used in terms of exterior insulation, 6 inches on the walls and 8 inches on the roof. All of the framing is heavy, 18 gauge, it says 20, but it's 18 gauge panelized framing. And that was, all of this is being off grid, and they're mild preppers. They actually wanted this to be there. They wanted to be completely disconnected from the grid, not for energy savings as much as just, being disconnected. So we used a sheathing or a gypsum sheathing, and then which is a dense element barrier system, which has an integrated water resistive barrier into it. It's like zip for gyp, and they have a liquid flashing that they apply to the seams and all the screw holes, all the screws, just so for continuity. We have a 20 gauge hat channels and then a 20 gauge corrugated metal cladding. So it's zero wood in this entire structure, fire resistant, mold resistant, and nothing for the termites to chew on. Obviously, we'd had wood trim and cabinetry and those sorts of things inside, but finding their way in there was difficult with an air change or with an air tightness like that. And again, this is the roof, 8 inches on top of, this is a little layer of gypsum sheathing and a corrugated metal deck. Under the slab, we have 4 inches of rock wool, of stone wool, about 4 feet in, and then 2 inches everywhere else. So the entire slab, the whole structure is wrapped in a stone wool blanket. These are the hygrothermic results for these assemblies. This shows 3 layers of 2 inch, but we ended up with 2 layers of 3 inch. This was our mock-up wall. So you can see the metal framing, gypsum sheathing, and that red goop right there. That's the liquid flashing. So here is our assembly showing the temperature at the sheathing layer. And then if we didn't do that, here we are, 18 degrees again. This is the project we're about to finish up here in Marietta, Georgia. And this is from one of the articles we did at JLC showing this assembly. You can see the whole slab again wrapped in insulation. We cannot use stone wool underneath the footer here, so we do use either XPS or EPS, and it can be borate treated or we treat it on site. And then we wrap on top of all the insulation here. You can see we go 4 feet in with 4 inch and then 2 inch the rest of the way. But the entire slab turned down is wrapped. And then we continue that insulation up. We did a liquid applied water resistive barrier here. These are our air and vapor control layers over a 1/2 inch sheathing, and then just wood framing, 2x4 wood framing. And so we've got, then on top of the insulation, we have a termite proof vapor barrier called Pango Wrap. And so if you seal it perfectly, you are going to, this is, what we like about this is not having to treat with chemicals the soil. So, and then details like this, super important. We've got a little Termaf tape here. We're sealing the gap here first, and then we cover it with a termite-proof tape, and then we overlap our air and moisture barrier here over the top of that, and then it overlaps this termite shield here. Also an insulation protector that we put in for construction, so as people go in and out through the exterior wall there, they're not kicking our insulation and destroying it and having to replace it later. So these are some shots of construction, both in Marietta and North Carolina, but we use this is borate treated here, and this is XPS that we treated on site with just a spray of borate. This is what it looks like going around the corner here from vertical to horizontal, and then we just and then this is them packing really, really well. Of course, getting our soil perfect was that's another discussion, but this is everything within 98% compaction rate. Here, just a shot of that turned down slab. This is just working our way up the assembly. So always the insulation 4 inches, type 6 XPS or EPS, which means it has a higher bearing capacity than soil does. And this is all this formwork here that is custom to this, and we have to, of course, to hold the insulation up, we've got these little spacers here. But this is what it looks like, the whole slab insulated. And then this is our vapor barrier. This is the Pango wrap here. This is not the Pango wrap. It's not doesn't have that termite resistance to it. But now this is all of our projects we're using this Pango. And this is the detail through a penetration there. We reinforce our slabs anywhere from 5 to 8 inches. We did all 8-inch slabs up in North Carolina, just because we didn't want any, just thinking durability long term. So we do rebar every 16 inches here in the middle of the slab. And then we protect our slabs with a non-perforated membrane, and this also helps the slab cure longer, which makes it stronger. So we keep this on until we're ready for finishes. And over time, it starts to leak through some of the seams as traffic hits it. But for the first 4 to 6 months of the while it's down, it is still holding moisture. Actually, 2 to 4 months, and it's still holding that moisture. And you can see it on the underside of this wrap. This is the 18-gauge metal framing, super durable, lots of 12-inch on center. And because steel and metal is so conductive, we really didn't want to consider cavity. That's why the continuous on the exterior was so important here, and why we did so much there. And then this is that sheeting layer with the integrated WRB, and the red is the liquid flashing. And you can see every screw is covered and every seam and corner filled up with this liquid flashing. It's our mock-up wall. They're just testing things out here. I always tell them, this is the time, excuse me, this is the time to mess up, not when we're actually doing it real. So go ahead and try away here and have fun. So then you can see all this is horizontal because we do have the metal cladding. It's corrugated 20 gauge, and they're working their way up. You can see fewer and fewer of these washers here because they realized they could just stack it and it held itself up until we got the furring strips on. So we build the walls first, and then we put the roof on. And you see we're staggering both horizontally and vertically. And then once the roof is on, we got our furring strips here, and then we started putting our roofs on. And here you go. This is what it looks like, kind of wrapped up there. So they were able to put all the insulation on before any of the furring strips, which worked out real nice for them. This is the house in Marietta. We do have horizontal here and vertical. This was because of the vertical siding that we had. This is also, like I said, climate zone 3A, got down to 0.05 ACH50. Here's the assembly. We went with two layers of 2-inch on the walls, and then two layers of 3.5-inch on the roof. And the reason for the 3.5-inch is we have outriggers that are 2x4 outriggers, so that worked with that dimension, and they're embedded in the insulation. So it was important to keep the assembly simple. And again, the continuity below, and so we go from wall to roof, same assembly. And we used polywall here, which is their liquid applied membrane. And we test our houses after we get this done. Then we do penetrations. We test it again, and that's for the air leakage. That's what the blower door is there for. And we went from 0.6 or 0.07 ACH50 down to 0.05 ACH50 from this stage to penetration, because we were able to identify during this stage where the leaks were. Then we addressed those, made penetrations, sealed those up, and we're able to get tighter, even tighter. And it's done by, this is our painter. So he was able to do all of this labor because that's their recommended application, is with the roller. So it worked out well. These are the outriggers that I mentioned. So these are 2x4s. You have all the 3.5-inch insulation. First layer fits in there. These are framed exactly 2 foot by 4 foot, which is the size of the insulation panel. And so these are the clips tie into the roof structure. And then we covered, this is on the underside of the back porch. You can see the insulation just continues so that we could keep the thickness and the profile of our roof. And it also helps with when she's out here on her screen porch, it helps with heat gain in that area on the exterior as well. So this is all these overhangs are built on top of the roof. And here's this canopy structure is built to the exterior. There's a bolt here and then screws through here, but none of the steel, this is a little rubber gasket here. None of it's in physical contact with the sheathing. This is our roof. All of these, we did all of for the roof furring strips at a 45 degrees to promote drainage. But they're lined up and they're attached through with 9-inch screws into the trusses and roof structure below. And this is a continuous core vent here for the drainage. You can see our gap there. That's our rain screen and ventilation cavity. This is the core vent up here. Allows the air to flow up and in through the cavity and up to the top side of the roof. Again, mock-up wall on every project, test to allow them to practice and mess up if they need to. This is we have a ventilation strip at the bottom and at the top, and anyway, so 4 inches here, and then the roof gets another 7 inches. This is what it looks like kind of right before we started cladding it. The canopies, of course, this is south facing, so that's why we have all these canopies, but we also have 4 to 5 inches of protection here because we installed the windows at the sheeting layer. We didn't build it out to be flush. This is called an INI window, so it helps with protection against the elements, but this also helps with that and the shading. So everywhere else that we have horizontal here, we have horizontal or vertical strips. We do horizontal siding. On the corners, we're using we're using fry reglet as metal trim instead of cementitious trim. And so we needed to have something horizontal here because insulation is here and the structure is back over here. So we had to cantilever this out, tie this into the structure so that it could cantilever out, and then we have something to attach to right at the corner. Just another shot here of And you can see none of the washers on this job. We didn't use anything because we had our first layer down here and we just stacked on top of it, and we got up to a certain level and they started installing these furring strips, and that ended up being what held the installation from toppling over until they were able to secure those furring strips. This is one that's been designed very similar to the off-grid home, except all wood construction. So the assembly is exactly the same, except we're using wood. So 6 inches on the walls, 8 inches on the roof. And so that's, there we are. That's just a few of the projects we've got going on. And so I'm going to hand it over to Dan Edelman here now, so for him to say a few words, and then we'll come back to me for a minute, and then we'll get to some questions. So Dan, take it away.
Thank you, Chris. And that was incredible. Really awesome, very impressive projects. Just so everyone is aware, this meeting is being recorded and will be sent out later to all the attendees. If you are new to GoToWebinar, there is a way to ask questions that we'll get through after this little presentation on this program. So Chris, I should have control of screen. Yep, I do.
Yep.
So really at this time, I wanted to discuss a new program that we at Rockwell just released. Chris is one of our many already enrolled in this great program. It's called the Rockwell Elite Builder Program. Before I get into the program, I did want to inform you of some of the new products that we just released. So we have a new product, Rockwell Comfort Bat line. So really nothing different about the product itself. It's really just new R values. So, these new products are code driven and will meet code with all the features and benefits of Rockwell. And like all of our products, they are still utilizing cross-directional fibers to reduce airflow, but without stopping airflow. And one of the other ones, especially for the southern climates, we now have an R38. So you can now have a single step application for attics and cathedral ceilings with a total thickness of only 9.5 inches. These are available now to be installed by your installation contractor or from your local installation supplier. Speaking of R value, Comfort Board 80 did just receive a higher R value per inch. It used to be 4 per inch, and now it's up to 4.2 per inch. So really getting back to the program, the Elite Builder program, you could see the design of this wall assembly and roof assembly. This is one of the many designs we have. We offer designs beginning with below grade, both sub-slab and foundation like you saw from Chris, all the way up to the roof like this design shows. Rockwell can also help our elite builders with these designs, increasing your confidence with proven designs and eliminating risk while producing a high performance and durable assembly. Please also reach out to myself for any other solutions. Let's say you don't have the budget or need to insulate the roof deck. I have other solutions with doing a continuous air barrier and going from basically the exterior of your wall and wrapping it inside prior to putting on the roof trusses. Some other promotional material that you get with this program. Basically, we just want to help differentiate the builder from other builders in your area. So, there is a Elite Builder Program brochure that you will receive after applying to this program. There's also homeowner pamphlets that educates them on the features and benefits of Rockwell, including indoor air quality, moisture resistance, sound, fire, and long-term thermal value due to no blowing agents or off-gassing over time. We also have showroom monitors available that show some of these features and benefits in a fun-spirited way in a looping video. The homeowner brochures also fit into this display. As you can see, some of the other materials, including literature and samples for you or your customers, so those are all available to you. We do also offer building science support and can do WUFI analysis for you, R value calculations, heat transfer modeling, overall U value, and even dew point calculations, similar to the ones that Chris was showing. These are all free of charge for you throughout the year. You can also receive promotional merchandise and wearables. To sign up, all you need to do, simply go to rockwell.com/elitebuilder and hit apply now. From there, you'll be in contact with either myself or a local territory manager to get you started on the program. So there is also rebate opportunities available. They do differ from United States and Canada. So you'll actually be able to kind of see, what the differences are. And again, once you apply, we'll send you all the different rebate packages for your country. So at this time, thank you again for joining this presentation. We did receive a few questions in the chat, so I just wanted to kind of, Chris, I'm going to be asking you a couple questions. So the first one comes from Cherie Dittmer. What finish material protected the closed foam board on the foundation walls? I believe this was pretty early on in the presentation, so I think it was the termite control, maybe?
On the foam, where if it's the rock wool we're talking about, yeah, we used, or if the stone wool exterior that we used just an aluminum flashing material to cover the insulation. It was custom made. It's just basically a Z flashing, and we put that on before we did our backfill and secured it to the foundation, the turn down slab, and so it doubled as the protection of the insulation and a termite shield. So that was it's just a I think 14 gauge aluminum painted.
Okay, and that was pretty much above the soil level, but below the comfort board and siding.
Correct. And then and so because there's a warranty requirement by the cladding manufacturers that, some of them want you to have 6 inches between the bottom of their cladding, bottom trim, and grade. We installed another piece of just flat aluminum flashing over to protect the insulation, and just for a decorative piece. And it was behind. It would kind of be installed behind the furring strips of the rain screen system, and then it went below grade. So that was it shows up. You see it, but it's decorative and protective.
Okay. And there was another question that actually falls right in line with this: is what cladding manufacturer, what cladding do you typically use on your homes? Is it maintenance free? Is it wood?
Yeah, it's always a low maintenance. So of the projects we've done, all of them have been either fiber cement, some sort of composite, or a metal, and we continue to use all 3 of those now. But it depends on the project. There are woods that you can get treated, and the way that they're made, they can be low maintenance. I think the main thing we're doing with all of them is designing details, designing the system so that we don't have a need for caulking or sealants where they're typically installed, because we do have a rain screen. Air and water can move freely throughout these assemblies, so we don't need
Chris? I think we lost Chris. Garrett, can you hear me? Hey, can you guys hear me again?
Yes.
Okay, sorry about that internet connection. We have virtual school going on here too, so apologize. So one of the other questions that we got was basically, how do you address the windows in the house with all the continuous insulation on the outside?
We have preferred over the years because of we attach it to the sheathing, and so the insulation just basically goes almost right up to the window frame on the exterior, and we leave enough of a gap in that between the window frame and the insulation to allow for the cladding to return and die into the sheathing. And so you install them just like you would on any house that doesn't have the exterior insulation, but the difference, and then allow the insulation to just run right up to it. We have not done the Audi window, which is you build up a box to push the window out to the exterior. And we prefer this way because it having the window pushed out, it creates ledges on the interior that most of the homeowners we've worked for are interested more, like they want more of the interior to be normal, and then the exterior having that recess gives us an architectural element of what we call a punched opening. So it pushes it back, gives us a little bit of a reveal. It looks nice. It's also protective to the window, so it gives us anywhere from 4 to 8 inches of protection at the top and the sides for shading, for water, so it's no different. The windows go on. We install a little bit with more fasteners and more goop around there just to make sure it's perfectly installed. But other than the normal installation, it's the same.
Yeah, and I'm sure also with having an any design, especially in the hot climate, reducing the solar heat gain from the window would also help. You guys also do the solar shades outside, but that also would help.
Yeah.
And then getting it.
It does. It helps. Yeah.
And then also getting it so your air barrier and water barrier are continuous without doing a window buck first is probably also much easier for a labor standpoint.
Yeah, there are a lot of products out there for insulated window bucks and things for continuous insulation assemblies, and we eliminate all of that, and we eliminate the origami for the water resistive barrier, all of those control layers at the window, by allowing the insulation to just stop right there. And the other thing about that is, typically on the interior of the window, where between the window frame and the rough opening, typically that's filled with insulation, to keep the insulation continuous. But because we don't have any cavity insulation, and because the insulation goes right up to the window frame, there's no need to try to fill that gap. We can just air seal it and be done.
Right.
So the insulation is still continuous without having to fill that little gap, which sometimes is paper thin, and sometimes is 1.5 inches wide. And either way, it can become a tedious, opportunity.
Yeah.
There.
Well, and even with putting all the continuous insulation, even in like a northern climate, now you're actually keeping the sheathing warmer, reducing the chance of condensation on the backside of the sheathing, because whatever your temperature inside is now is touching your sheathing on the exterior, but you're still well insulated outboard of that. So you're actually having almost a more durable assembly too.
Correct. And that's, mentioned it earlier, that we're trying to not only protect the occupants from, heat loss and gain from moisture, from air and all that, we're from bad air, we're protecting the structure. And if the structure is protected, it won't have the expansion and contraction. It won't have the degradation that comes from being exposed to the elements. And so over time, every element of your structure is protected for the life of the building, and that's what makes it durable, high performance, and that's what helps make it last as much longer, because you're not exposing exposing the structure, which is what keeps the building standing up.
Right. That's the most important part of a house.
Yeah. Failed buildings are bad for business.
So one of the other questions, quick question, what was the R value of the wall in Dade City tiny house? This was from Kevin Brennan.
The comfort board that we used has an R value of 4 per inch. And I mean, if you dig down deep, it'll say 4.2. What happens, stone wool actually can increase in R value as it gets colder, depending on the product. So I would say we had, just simplicity, we have an R8 on the exterior, and then our cavity bat, our cavity insulation was the comfort bat, and it was an R15. So,
Okay.
So the continuous R value is R8. And if you take out the studs and all that, that then ends up being about R11 for continuous. So it's R11 plus R2, we're about R8 and 11. So we're about R19 continuous.
Okay.
And that's a huge difference. That's a lot. I mean, building officials don't understand this. So we have assemblies with R30 at the roof or R34, and they immediately will tell us, no, that's not going to meet code because you have to be R38. But R38 is in a cavity, so they're not accounting for the 2x or the framing material, and so the actual R value, like the through wall R value is closer. Is below 30 when you have an R38 insulation, or closer to 30 at least. And so when you have continuous R34 or 35, that's it. That's your R value permanently. Whereas the others, you lose the overall R value of the assembly by including all of the framing, because each stud, or what it's R1, so it's just it decreases the overall performance.
Yeah, and when you're adding continuous on the exterior, you add an R8. You add R8 basically in an effective R value as well. So your R34
Correct.
roof is way over exceeding code at the R30 in the cavity.
Right. In Georgia, they allow us to do an R19 on the roof if you use spray foam insulation on the underside of the sheathing, like inside the assembly. Mm-hmm. And because it's an airtight, insulation, or it contributes to the air sealing, and also so they allow R19, but again, that's R19 with plus the loss of, or minus the loss of the framing. And so your continuous is below R19. And when we put 6 or 7 on the roof, we're talking about 2 or 3 times that, but they're not seeing that. They're only seeing that, oh, this is strange that it's on the outside and it's not R38, which is what it should be.
Right.
But they still allow R19 in between, framing members. So there's a lot of times we have to educate our building officials, and they're not always receptive to it, and they're not able to reach that. So, yeah.
Okay, and then another question from Ross Can. How do you prevent the furring strips from compacting the rock wool?
That's why we do the mock-up wall, because it gives our crew a chance to practice without compression. So they'll go through, I think on a mock-up wall, they probably put in 50, 60 screws. So they have that many chances to figure out how far they need to go. And a lot of times they'll just back it out if they go too far. Being a rigid insulation, it doesn't compress very easily. So when they can tell that they've gone too far, because they'll see it compress, and so they'll back it out just slightly. And so that's the way we control it. And then I'll walk around the house after they're done, and just keep, look for compression, and just have them back it out wherever they've gone too far.
Okay. Well, thank you very much, Chris. It's now 1:00.
Yep.
Anybody else
Okay.
that has asked questions, we'll definitely get back to you on them. Thank you for everybody's time. Thank you, Chris. That was phenomenal. I learned so much from you and your projects. And on the
Awesome.
screen now, you could see all of Chris's ways of reaching to Chris. He has social media, website, and email as well.
Yeah. 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 The YouTube channel has a lot of stuff, talks a lot about some of these projects and some of the, how we did it. So if anyone's interested in that. Thanks for having me, Dan, and everyone there at Rockwell. This was fun. I'm glad to be able to share it with somebody because doing it and all this time, I've got it in my head, and it's just nice to have somebody else interested in hearing what we're doing. So hope it was useful. Feel free to contact me if you have any questions.
Yeah, and likewise, if anybody needs to contact myself or interested in the Elite Builder program, you could go to rockwell.com/elitebuilder, or feel free to email me as well, Dan.Edelman@rockwell.com. Thank you, everybody, and have a great rest of your day.